Optimize. A journey through database query optimization. This course is filmed on location at Carnegie Mellon University in front of a live studio audience.
All right, so today we're going to pick up sort of from the very beginning of query optimizers, discussing the first implementations that happened way back in the 1970s. And in particular, the paper we're going to focus most on is one I had you guys read on System R, which I think is, I haven't read in a while and I forgot how amazingly good it is. Because, like, again, even though it's written in 1970s, you can still understand what they're talking about, right? Some of the stuff in the papers in the 1970s are get a little dicey because they talk about things that don't exist anymore, or like old machine things that nobody cares about, right? Man, you could take that paper, it's brilliantly written, cleanly written, and you can take that and re-implement it today. Can't say the same thing about a lot of systems papers back in the day, but that's a good one. And again, it's the foundation for everything we talk about this semester. All right, so last class we talked about course objectives and expectations. I will be sending out on Piazza the note-taking schedule tonight, so there'll be no assigned note taker in this class today. And then there'll be a spreadsheet. We put your Android ID and everything in, and then we'll get everyone credits on Amazon to run experiments and projects as well. If you're on the wait list, we'll process that after this class today. I think there's about 4 or 5 slots left, so we'll pick people off of that. Then we spend time talking about, just briefly, like why query optimization is an important and hard problem. And then today's class and going forward is really about how do you actually build the optimizers to solve it. So we're going to first talk about the high-level background of what was going on in the 1970s, other than cocaine, in databases that led us to having to build something like that they did in the System R paper. And then we'll see an initial approach that was done in a precursor of Postgres called Ingres, and the technique that they did, which is like stupidly clever, and it worked for the time what they were dealing with. But then we'll still again see how they apply the sort of the heuristics, even though the way Ingres can do join ordering is not how you'd want to do it today. The logical transformations they're going to apply, the rules, are going to be the bedrock for how we're going to do modern query optimization. And then we'll go from there and talk about how to incorporate the cost-based search from the System R paper. Okay. So in the late 1960s, we covered this in the intro class, but in the late 1960s, that's where or actually just 1960s in general, that's when people started building the first general purpose database systems. The first one I think was developed by GE for I think it was IDS, that was developed for a logging company up in Seattle, and then they said, oh, this is actually useful for other people, and they sort of made it a bit more general purpose. And of course, there was IMS that IBM built to keep track of all the parts for the Apollo moon missions as well, right? But the way people interacted with database systems back in the day was very much writing procedural code where you specify exactly what you want the database system to do to run your query and compute your answer. And the leading idea, the leading sort of, I guess, standard, if you will, was this thing called Codicil. And this came out of the COBOL movement. And there's this paper from 1973 by Charles Bachman, who won the Turing Award, like one of the first Turing Awards, like the second or third one, back in 1973, on his work on Codicil, on his early work in databases. And in his paper that he wrote as part of the, getting the Turing Award, it's this famous paper called the Programmer as Navigator. And it's exactly as you would think it sounds like. He goes on about Copernicus in the beginning and Galileo, ignore all that, right? But in later pages, he talks about how he envisions a programmer would be interacting with the database system and treating him as like a navigator. And he lists, like, here's 7 different options that he, of course, it's always sexist back then, but how he, the programmer, could navigate and interact with the database system, right? They could start at the beginning of the database and find sequential scan, have an index, do button lookups, right? So he's listing all the choices a programmer would have to make in order to write a query in Codicil to compute some answer that they want, right? And there's this little blurb here that says the synergistic use of the entire collection of these different options gives the programmer great and expanded powers to come and go within a large database, right? And so when you really think about it, think of how many different programmers there are out today, a bunch of JavaScript programmers. Do you really want them making decisions on the best way to navigate or find data in a database system, right? And so I had ChatGPT write this query for me in Codicil. I don't know if it's right. I can't run COBOL, so I assume it is. But this is basically the program you would write in Codicil to go do a lookup across 3 tables to get all the name of the artists that would appear on a mixtape album that we put out for DJ Mushu last year, right? To get all of those artists across 3 tables, you'd have to write a bunch of code, and you see a bunch of these nested for loops doing these lookups to find the things that you want. And so basically, we're explicitly defining the join order in this program of how we want to interact with the database, as Charles Bachman wants you to do. But of course, when you write this code, you're making a bunch of assumptions about what's in the database at this time. Therefore, you're using that to decide, going back here, which of these 7 options is the best way to go. But then, as we all know, data changes and evolves over time. New fields get added, new data gets added, values may change. And so what was a good idea when you first wrote this code, or ChatGPT wrote this code, may not be a good idea in the future. But now that program, that execution plan is hard-coded in this application. So if the data changes, or assumption changes, anything changes that would violate those assumptions, you have to go back and rewrite all of this. And good luck having time to do that, and then assuming that the person who wrote this program, this before ChatGPT, but the person who wrote this program is still around to even figure out, oh yeah, this is why I did it this way, right? If you hate debugging people's sort of regular procedural code, imagine having to debug their query code, right? It'd be terrible. And so the great idea of the relational model basically distills down what that program was and all those various steps in those loops into a declarative form to say, hey, here's the answer I want. Give me the artist names by joining these 3 relations together. We're not specifying what order we apply any predicates. We're not specifying the order we do any joins, right? The database system is going to be in a position to make the best decision about how to execute this, ideally, right? That's what this class is about. And so then as the data evolves, the query plan can evolve without having to go back and change any application code. So we covered the relational model in the intro class, and we made a big deal about having these 3 tenets, right? That there's this independence between the physical layer and the logical layer of the data, right? There's one of these integrity constraints to make sure that people don't insert stupid things or break our data, right? Or insert things that shouldn't be in there, right? But the big one is about how we're actually interacting with the database, right? Again, the original relational model paper that Ted Codd wrote in 69, SQL wasn't invented yet. This is all just relational algebra notation. SQL came around in 74 from the IBM people later on. Ted Codd then proposed his own query language called Alpha that no one ever did. But like the Berkeley guys, they invented Quell, which is, again, based on relational algebra out of this paper. But the core idea is still the same, that there's this high-level declarative language, or API, we're going to use to access the database system. And therefore, the database system is going to be in the best position to decide how to run that query. Right? So there was sort of 4 main early implementations of the relational model. The very, very first one, as far as I know, it was this thing called Peter Lee Relational Test Vehicle. That was done at IBM in the UK. And that one was an early prototype. That the guys that worked on invented SQL worked on that. The project didn't really go anywhere. They didn't commercialize it. It was a proof of concept. But then they went and moved to San Jose at the IBM research lab there. And that's when they started getting serious about building a relational data system. And that's where System R came out of, right? As I mentioned before, Stonebreaker was at Berkeley, and he took Ted Codd's paper and started building this thing called Ingres. If you ever want to know why Postgres is called Postgres, because it's post-Ingres. It's the second system after Ingres, right? And he didn't do SQL, he did Quell. Larry Ellison, the 3rd richest person in the world, and now he's on his 6th marriage as of last year, or a couple years ago. So he read all the IBM papers, thought this was a great idea, thought SQL was a good idea, and just basically re-implemented the same thing, and then became what he is today. And then there was another research system out of Sweden called Mimer that still exists today. It's now called Mimer SQL. But that was an early, SQL-based relational database system. So all these guys eventually had to build query optimizers because, again, Ted Codd's paper says that you want to have a declarative language. You want the data system to figure out the best way to execute it for you, and therefore you need a query optimizer. Now, I couldn't figure out what Mimer did. I think it was heuristic based, similar to Ingres. Oracle was going to be heuristic based for a long time, to the 90s, as we said last class. We'll see it again in a second. But System R, out of the gate, they said, no, we're going to do a cost-based search or query optimizer. and try to make the best choice. So this is a rough overview of all the different design choices you could have when building an optimizer. And we're going to cover all of these except for maybe the last one here. I talked briefly about it throughout the rest of the semester. But we want to start at the very beginning of like these heuristics, and because that's going to be these sort of hard-coded rules that we would have in our optimizer implementation to determine when we see certain patterns in our query plan and what transformations we should apply to end up with a good query plan. But importantly, they're not going to be based on any cost estimates, the way System R was. Right? That came later in late 1970s in System R. And pretty much every data system that has some kind of cost-based search is going to be based on the System R paper. Next class, we'll see the Starburst paper, and then that'll lead us into the Cascades paper. The line's going to get blurry between stratified and unified search, right? Because like Cascades in Microsoft is a unified search, but they do it in stages as if it's a stratified search. Right? So I'm less concerned about this distinction here, but this is what the literature, how it describes it. I'm going to care more about whether it's bottoms up or tops down. That's going to have bigger implications for the implementation. And then randomized search would be like simulated annealing, the genetic algorithm that's in Postgres that doesn't work. Right? Again, there's some prototypes that do this. Postgres is the only one that actually does it. And then we can talk about the neural network stuff or the AI machine learning stuff as we go along as well. All right, so let's start in the beginning. Let's talk about like what was the first query optimizer that they built in the initial prototypes. So the basic idea is that we're going to have hard-coded logic in our database system that looks for patterns in our query plan. Right? And think of like I'm operating on the logical plan that's coming out of the binder, and I'm converting those logical operators into physical operators. So I have these if then else statements that says if I see this logical operator maybe followed by this logical operator, then therefore I can do some kind of transformation. Right? This is basically how Postgres works today. If you ever look at the Postgres subplan code, it literally is a bunch of if then else's that they're just applying these kind of rules. Right? And again, the reason why this is going to work reasonably well is that we can apply domain knowledge we have about database systems to know that there's certain things you're almost always going to want to do, and therefore, if you see the pattern in your query plan that matches that rule, go ahead and actually do it, right? Like pushing down the most selective filters first, do predicate pushdown. That's almost always a good idea. So do that, right? Do all your scans before you do any joins. That's usually a good idea. Predicate pushdown, so forth, right? For join ordering, you could do really simple rules based on like just how big you think the tables are. Is that really cost-based? Sort of, but not really. Nothing. It's not really that sophisticated where you're deriving selectivity estimates out of operators or predicates. Like we'll see that later on in System R. As I said, this is what Ingres did in their first implementation, and I'll see in a second how they do join ordering. This is what Oracle did up until like the 1990s, and they claimed how great it was. But they obviously got rid of that and switched over to System R. And then Mongo still does this today. And most new data systems you see when they get announced, almost always are going to do something like this because building a query optimizer is one of the hardest parts, right? Again, back in the day, in the 1970s, when they were building this, the databases weren't that big. You read some of those papers. The System R paper didn't mention this, but like some of the other Ingres papers, they talk about, hey, wouldn't it be great if we could have a table of 100 tuples? That would be amazing, right? Like the table, the size of the databases were quite small. So and the complexity of the queries are not as sophisticated as they are today. So you could get pretty far with this. Even today, you can get pretty far with this. All right, so the key thing we're going to leverage, the why we can do these transformations, is that we're going to rely on the equivalency rules within relational algebra. And the basic, we're not going to go through all of them right now, but we'll talk about the main ones. But like the basic idea is that there are known rules and transformations that you can apply that will guarantee that the outcome or the resulting relational algebra expression you generate from modifying an existing one are equivalent, meaning they're going to produce the same answer. And because we have all these rules we can use in relational algebra, therefore we have some soundness or understanding of what transformations we can make and when can we make them. That doesn't prevent you from writing bad code and actually doing the transformation incorrectly, but at least from a logical standpoint, we know that the transformations are going to be correct. Right? And this is how, again, a heuristic optimizer can be able to figure out what's a good decision or transformation to make without having a cost model. like predicate pushdown is almost always, for the most part, predicate pushdown is always going to be a good idea. Therefore, do it. And because I know my relational algebra equivalencies will guarantee that the outcome is still correct, I can go ahead and do that. So the two ones we're going to care about in this class today are for selections and joins, right? And I've already said this multiple times. But basically, the idea is like we know that we can move around the predicates in our selection operators or scan operators on relations, and that it's still going to be correct. So when we have a predicate with a bunch of conjunction clauses, like a bunch of ands together, I can just break them up on the ands and have separate individual selection operators that I'm just daisy chained together, and it's still going to produce the correct answer. And this is going to allow me to start moving predicates around that maybe as they were written initially, they're just all together in the where clause. But if I can break them up, I can move them down different branches of the query plan to push them below joins or push them below certain operators. We can also apply the same technique for our expressions or our predicates to simplify them further. Right, so some tricks would be like if you have something like where x equals y and y equals 3, it's way faster to do an evaluation on a variable, like a memory location and a constant versus like two different memory locations and have to make sure that they're all they're synchronized. So if I recognize I have something like this, I can just convert the y variable in my first predicate to be x equals 3. I can put the constant in there. I can do other simplifications like x equals 1 plus 1. Some systems can easily just convert that to 2, so that if I'm scanning a billion tuples, I'm not doing 1 plus 1 plus 1 over and over again. Right? Even though that'll be in CPU registers, it'll be fast. It's unnecessary work, and don't do that. And then this is harder to do, and a lot of systems don't do this, is if you recognize that if you're passing in a constant where you're applying a function to do some kind of transformation, like forget this date here, extract out the year, and then do my comparison on this attribute, right? If I have a billion tuples, instead of me invoking the year function over and over again with the same constant, do it once, then substitute the value in, and that speeds things up. There's other games you can play, like moving the if the year clause is maybe on the variable, you can rewrite the expression to put it on the other side. All right, that's more difficult to do, but some systems can do that. And then the other one are joins, right? And the two big properties we're going to care about is commutativity and associativity. Commutativity just says that we can swap the order of relations in our join operator, and of course it's guaranteed to be correct. And you can do this for inner joins, outer joins, are more tricky. We'll cover that later. And associativity basically says I can do the swapping again, and maybe join the first two, swap that out, and maybe join the first, second, and the third first, right? I can change the order in which I'm doing the joins, and everything still works out. And the challenge is going to be, especially with joins, because we can swap things out in these different orders, that the number of possible join orderings we're going to have is going to explode. Now we're going to simplify things in System R, and in most systems that one, we're only going to look at binary joins, so just joining two tables at a time, right? If you have to do multi-way joins, then the number of join orderings you have can explode. But most systems can't do multi-way joins. And then you can have to deal with, okay, when the order you want to actually do the join. So I think it's been proven that, again, picking the right join order is NP hard, because the number of possible join orders you can have for an n-way join is what's called a catalog number. Like, a number is really big, but it actually has a name of it, right? So it's going to be too expensive for us to consider all possible choices, and then that's why we'll see this in System R. They'll make some assumptions to reduce this down, and in other systems, they'll do other tricks as well. So this is me somewhat redundant over what we did last class, but now that we understand, like, these are the relational algebra equivalencies we want to apply to do our transformations, we can see how we can apply these transformations for a given query plan as we go along. So the first thing for a given query like this, again, we want to find all the artists that appear on the tribute album, right? So if I just take the SQL query, run it through my binder that then generates a logical plan, it's going to end up looking like this, where again I have my scans and my tables, but I'm not specifying the access method or access path I'm using. I'm doing the Cartesian product to do the join, and then I just have this big fat filter up here that's just taking whatever was in my where clause and applying it all at once. So again, because we can want to do that to break up the conjunction clauses in our where clause, we can break that up to individual ones. So now we basically introduce a bunch of new filter operators, that each only have one predicate inside of it. I'm not determining the order here because I can't, because there's no cost model. I can't determine the selectivity, right? So I'm just going in the order in which they appear in the SQL statement. So now that I have these individual filters or individual predicates, I know I want to do predicate pushdown. I can then apply transformation rules where if I recognize that I have a filter clause that's referencing just one attribute, like attribute.name equals something, then I want to push that predicate down to be right above wherever the scan is for that relation, right? So I can move down the lookup on album name down here, and I can put the join predicate here, put the predicate for the join right above the Cartesian product here. Again, I can just do that by looking for going back here, identifying that if I see a predicate, and then I have a rule to go find me where I'm doing the scan on that table or the join that's being referenced in the predicate, and putting it to be right above that logical operator. Now I can do another simple rule that says if I have a predicate followed by a Cartesian product, and the predicate is referencing both sides of both relations in my join, then I can just collapse down and convert the predicate and the Cartesian product into an inner join, right? And then at the end, I can do, if I see I have additional attributes that I'm passing up that I don't need, then I can just do a projection push down and add the projections so that I'm filtering things out as I'm going up. Again, depending on the implementation of the system, whether or not it's a column store or a row store, whether it's single node or distributed, you may not want to do this. If your table is really wide, it makes sense. If it's not that wide, it doesn't make sense because you're just extra copying. But again, I don't need to look at the cost model. I don't need to look at any statistics to determine to do any of these operations. It's just sort of hard coded in the system. If I see this, then do that. All right, so this will give us a reasonably optimized query. But of course, then depending on how big these relations are, I may actually want to do a join in a different order than I'm specifying here, right? In my from clause, I have from artist appears album, and so the join basically is just going in the order that they appear in the SQL statement, right? But that may not be the optimal thing. So if I don't have any statistics, how am I going to figure out the right join order? Well, the way Ingres did it was they would just literally run every query. They would literally just run the query over and over again in multiple steps and just mash the results together. It wouldn't end up being the right order, but at least it would allow you to be able to do joins, because the first version of Ingres in the 1970s couldn't do joins. So say we had that same query before, but now we're going to add this order by clause from the artist ID. So the very first thing we need to do is take this query and we're going to break it up into what we'll call single value queries or single relation queries, right? So in the first case here, I'm doing my lookup on the album table and doing lookup on the Mushu trivet. I'm going to take the output of that first query, write that into a temp table. Then now I'm going to substitute where I had the album table in the initial query. I'm going to replace it with the reference to this temp table. Then I'm going to do that recursively again. I'm going to take this now it was a this three relation query, and I'm going to break it up into new queries that are each accessing just one real relation, so peers and artists, and doing the join against the temp table that was materialized by the previous query. Right? Now that I have this, I can actually just run the queries. So I'll run the first query, take the output of it, and then feed that into the second query, run that query, take the output of that, and then feed that into the next query. Right? So the first query runs, you get album 99 as the value. Then I just substitute that in for the album ID I'm doing my lookup on now. Now it's a single relation query. I'm good to go there. All right, and do the same thing now. Now I get two values here. So now I'm going to run this query twice with two different values, and then I produce my result. So they can't consider the join order. And this, if you're going to run joins this way, the only logic they would have is they would recognize that the entry point into the relations, if you will, is the one where you have a predicate on something, right? Because otherwise you're doing a Cartesian product against everyone else. So because I know I want to do a lookup first to get the album name here, that then gives me the album ID that I can then inject into the additional queries to produce my result. So I'm saying, so well, I'm showing this at the SQL level, but they would actually do this at the logical plans, again, using if then else's, but I don't want to show code for this. And so again, it seems kind of crazy to want to do this way, but if you start doing, one of the things we'll be able to do now is, instead of trying to do all the logical transformations on the 3-table join query at the very beginning, if I decompose it into now these single query or single relation queries, then I can do all the transformations to produce a reasonably optimal plan for just this one query. Now, globally, it may not be optimal, but for each individual one, it'll be close enough. So again, I don't think any other system actually would do it this way now today, right? Because it's just so inexpensive. But you'll see remnants of this, like you'll see in like MySQL, for example. For sometimes for a nested query, the optimizer will say, okay, I see a nested query here. Let me actually just stop the optimization process, go execute it. Right, so recursively call itself to get a new query plan for that inner query, run that and get the result, and then inject it back into itself. Right? System R does the same thing too. Right? That's the last section of the paper that they talk about. So to do join operations like this, it seems crazy, but there's other systems actually apply the same technique for nested queries today. That's not the right way to do it, and we'll see how the right way to do it later on. But I think again, it's a clever idea, and they're working under the constraints that they had at the time. All right, so any questions about this? Again, the key thing here is what they're doing is that there's, in the implementation, there's if-then else statements that are looking for patterns in the query plan. And if it recognizes them, then it calls some subroutine or some function to go ahead and do some kind of transformation, either from a logical to logical, but oftentimes mostly logical to physical. So it works reasonably well for simple queries, and actually it's going to be pretty fast, right? Select star from table where ID equals 1, 2, 3, assuming I have a primary key on ID. This can work just fine, because there really isn't any other optimization you want to do other than just picking the primary key index, right? So if you don't have to fire up a whole cost-based search algorithm, then this is going to be quite nice, right? And again, that's why most systems, when they first come out, they do this, because you can get something up and running pretty quickly. The challenge is going to be, and this will be a constant theme throughout the entire semester as well, is that it's going to rely on a bunch of magic constants to determine whether something is going to be a good idea or not. And in most cases, they're not even going to have this. They're going to say, oh, I'm always going to want to do it, right? Because they can't sort of look multiple steps ahead and say, if I do this, what are the implications of it? They just always do it. And then certainly once you start doing more complex things, you end up with a bunch of spaghetti code that's looking for a bunch of if-then else statements that are looking for certain patterns. And now implicitly in your code, the order in which you apply those transformations is the order in which they appear in the code. And that may not always produce the best result, because you may want to have more dynamic priorities to determine in the order in which you want to apply transformations. System R is not going to be able to handle that, but we'll see that later with cascades, how they do handle that. So I always like to bring this up. I mentioned this last class about Oracle, right? So this is from the semi-authorized biography of Larry Ellison that came out in the 90s. But they interviewed Stonebreaker. And Stonebreaker has some choice words for Oracle and Larry Ellison, but we can ignore all that. But in particular, they talk about the query optimizer. And he says that back in the day, Oracle had a really stupid optimizer. And their join order would be in the order that they appeared in the SQL statement, as I said before. But since Larry Ellison was an amazing marketer and still is today, he would go out and say, oh, no, we don't have, the other people have a semantic optimizer, like a cost-based one. You don't want that. What you really want is a syntactic optimizer, where you're embodying the intent of the programmer, because they wanted the join order that way, because that's the way they wrote the SQL query, and that's the best way to do it, right? And it worked until they realized that they weren't able to cash the checks. The marketing could not keep up with, or the engineering could not keep up with the marketing, And then they threw it all away in the 90s when Oracle almost went bankrupt, and then fixed it all. And they eventually switched to the system R approach we're talking about now. So I highly recommend the biography. It is hilarious. And then the computational biology department here, they renamed it two years ago, right? What is the name of the comp bio program here now? Anybody know? Ray Lane. Who is Ray Lane? Ray Lane was this former COO at Oracle that Larry Ellison hired to go fix the company in the late 90s or early 90s, right? And so he came to CMU, and I go talk to him like, hey, in the biography, how much of this is real? And he's like, it's real, but Larry made sure that he got all the things he wanted to get in there, and all the things he didn't want to get in there are not in there. But it's still, even that's still very entertaining. I highly recommend it. Okay. All right, so that's the heuristic optimizer. And again, the idea of using heuristics to guide us towards a better query plan, at face value, it's not a bad idea. And actually, you are going to want to do that. But just the key thing to get out of it, the way it's implemented in these early systems and some other systems like Postgres, through procedural code that is like if then else, that's not the way to do it, right? You want to have a higher level of abstraction. You want something to be, I don't use the word declarative, but like you want to have you want to be able to define the rules and have your optimizer determine on its own in which order it wants to apply them, right? If it identifies a match. And that'll get us down to the subsequent choices here. Okay, so I think the Ingres paper came out in 76, 77. And so at the time, again, this is how pretty much everybody was doing query optimization. And then we come over to the paper you guys read, which was the groundbreaking work on how to do cost-based query optimization based out of System R. So the basic idea is that they're still going to do that initial phase we saw in the heuristic-based approach. And as far as I know, in the case of System R, it was also a bunch of if-then-else statements as well, similar to what Ingres did. The key thing is that then when they want to start converting the sort of logical plan into a physical plan, in particular, figure out the join order for the relations in the query, that's when they're going to use a dynamic programming algorithm or a cost-based search to determine the right way to do this. And so again, the background of the System R project was like 15 people, all brand new PhDs at IBM. They said, hey, here's the TED Cod paper, go actually build it. And what's amazing about it is everybody had a PhD in computer science or mathematics, and they all sort of carved off one little piece of the system. Like one person, two guys worked on inventing SQL. Boyce and Codd did that, or Chamberlain as well, because Boyce died. Boyce died in 73, 74. But it was Chamberlain. Don Chamberlain created SQL. Somebody else worked on the cogen engine, the storage layer. And so one person, Pat Selinger, she worked on the query optimizer, right? She's brilliant. She did her undergrad and did her PhD in applied mathematics at Harvard, right? And this was like sort of groundbreaking work. And what was sort of controversial at the time, maybe not so much when the paper came out, but like when they were building this thing is, the same arguments people were making in the early days of Unix about high level programming languages like C, how the idea that you're going to rely on a compiler to then generate assembly code or machine code that would ever be as efficient as what a human could write themselves. That's the same argument like the Codicil guys were making back in the day as well, that like there's no way a database system is going to be able to generate an optimal query plan that does as good or better than what a human could ever generate in writing queries in Codicil. And so Pat Selinger basically said, no, like here's how you can do it, right? So that's why sometimes you'll see in the older systems, actually Snowflake calls it this as well, instead of calling it the query optimizer, like I am calling it this semester, they'll call it the compiler, right? Because that's a remnant of the 1970s about this idea of the compiling high-level languages to lower languages, right? So they had the same concept in SQL. So again, this will be System R. The first version of DB2 is going to inherit this work. We'll cover that next class. But then they'll get rid of that and switch over to Starburst, which you guys read for next class as well. This is also confusing because there's 4 versions of DB2. We'll cover that as well next class. Some of them use System R, some of them don't. And like I said, most open source systems that are out today are going to be using this technique. And again, the paper itself is very well written. You could take and actually sit down and actually implement it. All right, so we've already covered this before, but the core idea is, again, we want to convert the logical operators into physical operators. And the big thing that they're going to have to do is figure out what join algorithm they're going to want to use, what order that they want to apply the joins, and then in what cases are they going to have to spill to disk and materialize temp tables sort of going from one operator to the next. And to do all this, again, they're going to rely on a cost model, right, to estimate what the expected amount of work the data system is going to have to do for the physical operators in the query plan. So the way they're going to break the problem up is that they're first going to break the query into what they call blocks. And we'll see this idea again in Starburst next week. But they're going to break it up to what they call a block, which sort of represents a select clause with a from on a single relation, and then or one or more relations, and then some kind of where clause. You can also have aggregates and group bys there as well. So it means if you have nested queries, they're treated as separate query blocks. You're going to optimize separately. And so they're first run all the heuristics we saw before to generate for each of the logical operators in a query block. They'll go generate the physical operators for them, and then including generating all the possible join algorithms you could use, the physical operators, and all the access paths. And then they're going to do a simple greedy search to figure out the access path to use for every single relation, and then the dynamic programming search to find the best join ordering. All right. So the first thing I got to deal with is what if the query block only contains one relation, right? And I think this is where the term comes from Sargent. I think they invented it, but I might be wrong. I think it's one of the earliest papers that talks about it. But they mentioned how, like, in this case here, if you identify that the query is sargeable, meaning the where clause specifies attributes that you can then use to do lookups on index data structures, then you can then examine all the possible indexes that could be satisfied by those predicates, and then you use the cost model to determine which one's going to have the lowest cost, right? So sargeable just means search argument able. Again, thinking like select star from table where ID equals 1, 2, 3, and you have a primary key on ID. That's a sargeable query because you have the ID value, and you can do the equality lookup on the index to go find the data that you're looking for, right? So if you take this example here, that doesn't match the predicate. Assume it's the same, right? I have this predicate here on the value. So I can either do a sequential scan, which I think the paper calls a segment scan, but same idea. I can do a sequential scan on the table itself, or I can do a lookup on the index to go find the data that I'm looking for, right? And you sort of think, like, again, at this stage here, you're just trying to determine, should I do a lookup on the index or should I do a lookup on a sequential scan? And they're going to rely on this internal cost model to determine is one of those choices, or one for all my possible indexes, are any of them actually going to be better for me than doing the sequential scan? And the way they're going to compute this cost is through this really simple cost function that they have, where it's just cost equals number of page fetches, which is the amount of I/O I expect to do, times some plus some weighted factor of what they call RSI calls, which is that's just a proxy to represent the amount of CPU work you're going to do. Because as the paper says, in their evaluation of the system, they find most of the time is being spent on this, basically the execution layer, doing the lookups on that. So that's a good way to determine whether how much CPU you're going to do. And obviously, depending on what the hardware is, you could change this W weight so that you're more if the CPU is more expensive than the IOs, then you change that weight. If it's less expensive than the IOs, then you change it accordingly, right? And that basic idea of comparing storage IOs or IOs versus CPU, that's pretty much how all systems use today. Yeah, you can throw in network, but that's basically more IO. There's more sophisticated things you can do, but I mean, this is what basically Postgres does, right? If you go look at the Postgres documentation, this is from an older version because it's simplified, but you can see basically there's a random page height cost, right? And you set that to be relative to the sequential scan cost for a single page. But then there's some CPU costs, like CPU tuple costs, index tuple costs, right? And these are all relative to the, again, the sequential scan cost. So if your CPU is slow and your disk is really fast, you jack these things up to account for that in your cost model. And it works reasonably well. This is Postgres version 8. If you go to Postgres, what are the latest one, 17? It just, there's like 6 more of these, right? Again, so it's like this, I don't want to go down too much of a tangent, but like this is, they're assuming that a human, an operator, an administrator, understands the relative trade-offs between I/O and CPU and would go ahead and set these things accordingly. Most people do not set these things accordingly. Just use whatever the default is, right? So in this case here, the default is that the random page cost, random I/O for reading a page is, sorry, the sequential cost is 4 times more expensive than the random cost. Yes. Yeah, you think that, right? For a startup too, right? Yeah. It works if you know. Sorry. All right, did the algorithm work? Does the machine learning work? Yes. Did the business work? Sort of. Not to the extent that we wanted, but of course other factors happened. But we can take that one offline, right? But again, the main thing I want to point out is like, again, 1979. She's basically saying it's page fetches plus CPU. Boom. 2025. It's the same thing, right? Because it's the fundamental cost of doing work in a database system. Now, Postgres, for great as is, this is actually pretty primitive. We'll see in the commercial systems, their cost factors are way more complicated. Like DB2, when you turn it on, it'll run basically a bunch of micro benchmarks to get these values for you, right? Including network I/O, and then they figure that out on the fly as things go. All right, actually, going back here, so the way they're going to then determine, all right, well, how many page fetches am I going to do? How much I/O am I going to do? Are going to be based on these formulas that they provide that talk about the different use cases. Like, am I doing a quality predicate on a unique index and I need to get one thing? Okay, here's the cost for that, right? If it's a clustered index or sequential scan, right, they have different formulas for all of these. And the way these formulas are going to work is based on what they call the selectivity factor, which is just going to be the probability that a certain tuple or tuple in your table, your index as you're scanning, is going to be satisfied by a predicate and therefore be emitted as output of an operator. And then the cumulative cost of all of those outputs going from one operator to the next is going to determine what is the total cost of the query plan. So the selectivity factor, as I said, it's based on what the predicate is going to be, and they provide, in the paper, this whole page of here's all the different formulas that one could use to derive the expected number of tuples that we scanned and emitted as part of an operator or a predicate based on statistics you collected from the data, right? Remember, the catalogs maintain internal information about here's what my data looks like. It's either when it gets bulk loaded, or if you're in Postgres, when you run the vacuum, that basically runs scan and updates these things. You can explicitly call analyze to update the statistics. But every single data system that's doing cost-based search is going to have to maintain some information about this. Now, this seems fantastic, right? Because now I can say I have these analytical formulas that I can apply on data I've collected about my data. I look at my predicates and I understand how they fit into these formulas. That determines, I can use that to determine how much work I think I'm going to have to do. Of course, the challenge is going to be is that there's a bunch of assumptions you have to make about what the data is going to look like, because the summarizations you have, the statistics you've collected, are never going to be perfectly represent what's in the data. So in particular, for the most simple thing, like something equals something, they have this little disclaimer here. This assumes an even distribution of tuples among the index key values. We know that's never going to work out in the real world, right? Just think of like where people live in the U.S. on zip codes. There's way more people living in LA County than anywhere in Montana, right? And so if you're trying to do a lookup of people on a given zip code, that distribution is not going to be uniform. So I'm pointing out this one because it's the most obvious one, and I think this one here, f equals 1/10. Like if you don't have any statistics, it's just this. It's a hard-coded value. And you laugh, but like you see this shit all the time in other systems, right? Because it's better than returning nothing. So yeah, so even though these formulas are sort of again the textbook definition of how you would actually implement a cost-based or a cost model in a data system, it's going to rely on these assumptions to simplify the problem that aren't going to work out in the real world. All right, so I want to give a quick demo of Postgres and see how it can pick selection predicates as well. So I have a really simple table. Can we see that? Is that okay? I think, yeah, okay. So I have a really simple table here that just has 2 columns. It has an ID, which is just incrementing by 1, and then I have a random value, right? So I've created an index on it, and we can see how well Postgres is going to be able to pick out in what when can it use the index versus having to do a sequential scan. And I think there's 10 million tuples. Let's see. Right, yeah, so there's 10 million tuples, right? And the values, the value field is completely random. So again, we can put explain in front of our query plan or our SQL statement, and we see what Postgres is going to want to do for the query plan here, right? So in this case here, I'm doing select ID from XXX, where the value is basically in between some range. And then Postgres can recognize that, oh, okay, that I have an index, like again, the chargeable query, that I can recognize, I can use for this where clause, I can use this index. We can more of this recheck stuff here, but the key thing is that it picked out the index, it decided to do the index scan that it should to do this query run as fast as possible. Okay, so what if I do something like give me just the 10 most or 20 the top 20 values within my table. Again, same thing. Postgres can recognize that, oh, if I can use the index to scan to one side of it and just iterate over the leaf pages and get the 20 tuples I need, right? That's going to be way cheaper than doing a sequential scan, so it chooses that. Problem is, again, like this seems, again, for basic things, this is fine, but Postgres is not going to be very smart and understand and be able to do anything for queries where the attributes that you're trying to order by on are not just referencing the column by itself, right? So again, the value is just an integer. But if I do something like this, if I play order by value plus 0, right? It's the identity. It's the same thing, right? What happens? Postgres freaks out because it's trying to do really simple rules to identify that, oh, I should, if I see my column in my order by clause and I have an index on my column, and go ahead and use it. As soon as I throw an expression, which is meaningless, the plus 0 is useless, it doesn't pick the index and it falls back to a sequential scan, right? So what I'm trying to say here is it's not just simple pattern matching to say, oh, if I see my column in the order by clause or whatever, or the where clause, let me go ahead and just use it, right? The query optimizer needs to be more complicated, more sophisticated, and understand and actually basically evaluate sometimes what in these different clauses, the where clause, the predicates, even before running the query to determine what the right thing to do. Right? I show my simple example before, where it converts like x equals 1 plus 1, and you can rewrite that to 2. Sure, that's fine. You can do that in some cases. But what if there was like a function in there, right? That just returned 1. Could it do that substitution? Postgres probably couldn't. All right, so I don't want to like dunk on Postgres entirely, but like we try the same thing in DuckDB. So here's the first query. Again, ID equals greater than 123, less than 456, right? It picks out the index fine. That's good. But now if I try the one with the order by clause, I'll set the limit to 20. And for whatever reason, it doesn't do the sequential scan. Or sorry, it doesn't do the index scan, it does a sequential scan. And then if I do the same trick before where I put the plus 0, or I've tried playing around with like trying to make it ascending, descending, it doesn't seem to want to pick the index. And I do that and nothing happens there as well. All right, so let me show you one system that can do sort of this partial evaluation of the search arguments for the clauses to figure out what indexes are the best access path to use, is actually SQL Server can do this. ClickHouse. Yep. All right. So in SQL Server, to get you don't run explain. You have to run this show plan all on. Right. You turn that on, and then now you'll start seeing stuff. So let's do the first query with the between clause. Right. And you see that, I mean, it keeps going way over there. It doesn't. Not really. The main thing is, again, it's able to do the index scan, right? What they call an index seek. But now if I do that, the top 20, all right, again, instead of a limit clause in T-SQL or the SQL standard, you should put the top function in the front, right? The key thing here, it picks out the index, uses that, you can tell the name the index it's using. That's all fantastic. That's fine. So let's do the thing that Postgres choked on and run the I can't read that. Let me see if I can highlight it. Yeah, there's a +0 in there. Right? And lo and behold, again, it's to be able to compute the scalar define and still use the index. Right? So again, the main takeaway for this one is saying, like, picking the, for the chargeable queries, isn't it enough just to do simple string matching on column name, and in my index? Fantastic, use that. There's a little more work we have to do. Now, whether that just happens in the binder or in the query optimizer itself, it does, depends on the implementation. But again, it's a little more work to do to actually pull out the right index that you want. Okay. I didn't try MySQL, but I assume it's the case, and I couldn't get ClickHouse to pick an index for me, or you always use the index. I always want to do sequential scan because I think it's only 10 million records, and I suspect DuckDB is doing the same thing. Like, oh, I can rip through 10 million records real quickly, no problem. Okay. All right. So related to this, for the order by clause as well, is this notion of interesting orders, right? And this means that it's the required order you would need to produce the correct result for the query. And so they talk about how when they do an examination of a block, they identify what is the required order output, either defined by an order by clause or a group by clause. The reason why they also include the group by clause is because, again, this is 1978, 1979. Hash aggregations weren't invented yet, right? So the only way you can do aggregations is through sorting, right? Like hash joining, I think it was 83, 84. Right, I think there's other papers about, like, we tried hashing and it didn't work, so they only did sorting, right? So you got to have things in the right sort order. So you need to look at order by clause and the group by clause, and then you keep track of for each query block what those required orderings are. So then now when you try to figure out what's the best access method, either index scan or sequential scan for a given relation, if the query block requires the sorted output to be sorted, you keep track of both the best access path that gives you the result in the sorted order you want, and the one that doesn't. And then you do a simple calculation, say, for the one that doesn't produce the sort order that I want, if I add a sort clause to or sort operator to it, is that cost going to still be better or worse than the one that produces in the correct sort order? There's sort of like a hack to tack on that they recognize that things need to be sorted to produce the right result. So they just add this extra step at the end to make sure, am I coming out correctly or not? And then we're going to see the same thing when they do joins. All right, so now to do joins, the join ordering, it's basically a three-step approach where you're going to first do, for every single relation you're accessing, pick the best access method, and then do basically all possible combinations of joining all possible relations you have in a query block. And then you sort of iteratively build up the query plan by then joining the next relation, and so forth, until you end up with the result that you would want. Okay, remember, we made this distinction between the bottoms up versus top down. And this is the bottom up approach where you're adding the join order, the join operators incrementally going up until you join all the things you need to join, and then that allows you to identify the one that has the lowest cost. And so just like before, where we were applying domain knowledge in our heuristics to find good query plans, they're basically going to do the same thing to prune the search space, because again, it's an NP hard problem to figure the join order. So I don't want to examine everything. So they do some basic heuristics to throw out things that they pretty sure they're never going to need, right? You almost never going to need a Cartesian product, so you delay them or don't look at them at all. And they're only going to look also like left deep trees. So that even though maybe the true optimal plan is bushy joins, they're, because the hardware is so simple and the problem's so hard, they're going to only consider left deep. Right deep trees are equivalent to this. There's no distinction there, right? So they just only look at the left deep trees. All right, so step one is do what we did before, where we have a single relation, or just figure out what's the best access path that we're going to use for that, right? And again, by looking at what are the interesting order are we would need, what indexes I have, just doing the basic cost calculations we have. Then now we're going to enumerate all the join orderings for the one relation plans to produce the best, using their best access path in step one to figure out for two relations, what's the cost of joining them. And then you pick the best one for each that level, and then you consider, okay, now if I add more joins to it, what's the cost of those? And you just keep repeating this over and over again until you end up with the final result. And what's going to be different about this approach than the top-down approach, we'll see later on, is where we have to maintain this memo table to keep track of the things we've tried before. We don't need to maintain any history when we do this approach, because implicitly the path that we've followed along to get to some level in the search tree is going to tell us what the history was that we care about. Whereas again, in the Cascades top-down approach, it's everything we've ever done before, because we want to avoid doing repetitive work. All right, so let's see a two-step visualization of this. Same curve we had before. All right, first step is choose the best access path for each table. And again, I would look at my catalog, use the formulas we had in the paper to determine what the best access path for each individual table. In this case here, for artists and peers, we do a sequential scan. For album, we do the lookup on the name, right? Because we have that as a predicate there. Then we're going to enumerate all possible joins. Because this is PowerPoint, it's not going to fit to do all of them, but I'm just assume this thing just all possible combinations that I potentially have. And then now we're going to determine for two tables, what's the best one, and then add another table, and then keep building that up to our final result. So this is the dynamic probing approach. Again, it's a sort of divide and conquer. We're breaking the problem up into smaller steps, solving the first step before we move on to the next one. And we don't have to backtrack in this case. So again, we start at the very beginning with the bottom. We say we have three relations. We don't know how we're going to join them. We say we know we're going to want to join them. So the edges emanating out of the sort of the logical operator, we're going to point to these physical operators that are going to say what join algorithm I'm going to want to use, and in what order I want to apply the join. I'm showing what the predicates would be here. And again, think of this thing going all the way out beyond the slide here, but to make it fit and be readable in PowerPoint, I'm truncating it. So then now, at this level here, right, for each of these logical operators after doing the join, right, either during appears in album appears, artist appears in album, and so forth, right, I'm going to choose the path that has the lowest cost, right? So say it's the nested loop join for all of these, and that one's the merge join, right? And then now for each of these logical operators, I'm going to say, okay, well, let me go now do the last join I need to do for the remaining relation, right? Do the same thing. Do all possible permutations of them, all possible permutations of the join algorithm that my system is going to support. And again, in the paper, they talk about they only have nested loop join and merge join because hash join wasn't a thing yet, at least not in system R. And then same thing here. At this point now, for each of these, go from this logical operator to the final result, I'll pick the one with the lowest path. And now I just do a backtrack and sum it up and say, okay, from getting one path to the next, which one is from the top to the bottom, which one has the lowest cost? And that's going to be the optimal join ordering for this relation, like the optimal physical plan for this query. Now, in this case here, remember that my query had an order by clause on artist ID, right? But the logical plans don't have any notion of sorting properties in the physical data. So again, they're going to do that same trick before, where they keep track of what's the best plan I had, where it was guaranteed to be in not sorted and sorted, and then see whether for the unsorted one, if I add the sort clause, is that going to be better than the sorted one? And if yes, I choose that. Otherwise, I choose the one that's already sorted. Right? Now, again, we'll see this further on in next week. Keeping track of what the physical properties are in our query plan as we're doing planning. For sorting, it's one thing, but there may be other things that we want to care about too, especially if you go into a distributed environment where things are actually physically located, right? That'll be challenging. And then again, we'll see how the cascades and the cascades approach is going to handle that. So I said this last class, and this is the key distinction we're going to care about most in this entire semester. Is it going to be bottoms up or top down? And so what I just showed you is the bottom up approach, right? You start with nothing. I know I want to join three tables. I don't know how I'm going to join them and don't know what order I'm going to join them. And I iteratively add pieces or generate new physical operators that I put into my query plan to get to my final result. The cascades approach we'll see in 2 weeks, that's going to be top down or transformative, where you start with the final result and you make permutations to the query plan to add the physical operators you need to get you to that result. Right? So it's like sort of permuting an existing plan. And then the additional readings we're going to have in the lectures going forward, again, we'll spend one day, will be here's the top-down approach, and the next day, here's the bottom-up. Yes?
How can you do something that considers plans but it's bottom-up?
Question is, how could you handle bushy plans and do a bottom-up? You just, going back here, you just add more. Yeah, you just add more. Yeah, add reverse. Right? So for this one, it's 3 tables, so it's always going to be right. But say there's 4, right? So say I join artist and album, and then I have a peers, and then the 4th table. So then I could swap that, and then have the physical operators that I'm going to consider coming out of the next logical operator would be just joining those two tables by themselves. Yes. Yes. And just makes it wider. And yeah.
Yeah, but then that would be that case.
For 3 tables, it doesn't make any sense. All right, bushy joins, again, it just means that like left heap join, I'll do 2 table joins, and then the output of that join is then joined with another table, right? And I always do that. I'm always taking the output of one join and then joining with another table. In a bushy join, you could take 2 tables over here, join them, take another 2 tables, join them, and then you do a join between the 2 join outputs, right? And in some cases, that's better to do. Back in the 1970s, they didn't want to do that because the hardware was so slow. So, because what would happen is if I do a bushy join, I do the first join, I got to write that out to disk now because I need to make space to do my next join, right? So I swap all that out to disk. Then I do the next join for these other 2 tables, and then now I got to fetch in the first join output to then join with the second join output, right? Whereas if you only do left deep, then you can do pipelining. Back in the day, oftentimes that is the better approach, but not always. Okay. So the last one I'm bringing up is nested queries, and again, this can be very similar to the Ingres thing I talked about before. And I should preface to say, like, don't do this. Like, this is not the way to do it. This is what MySQL still does sometimes. But this is the wrong way to do it, and we'll see how to do it through joins and rewriting from the German way later on. And we'll spend a whole lecture on it. But basically, they would treat the nested queries as all separate queries, like with a separate query block. And System would then identify the dependency between the query blocks, where one query was being fed into another query. And then what they would do, they would extract it out, the nested query, run that through its optimizer, right? To do all the things, pick the access path. If it's doing a join, do the join selection as well. And actually literally just run this, right? So pause the query planning on the outer query, run the inner query, produce some result, and then either substitute it back into the outer query where it's actually being referenced, or in some cases, if it was like a multi-value query, then just put that as a temp table and then do a join against that, right? And again, this paper is one of the earliest papers to discuss execution strategies for nested queries, which is basically was an unsolved problem for 40 years until the Germans came along and handled it. But the paper they wrote that we'll read doesn't handle everything. The new paper coming out literally a month from now supposedly handles all possible corner cases you have for nested queries. But I'm just only bringing this up to say that, like, again, they were sort of breaking a complex query up into smaller pieces and then running them separately, very similar to the way what we saw in Ingres. Okay, so the advantages of the sort of the system R style of a heuristics plus cost-based search is that you can find a pretty good plan in a reasonable amount of time without having to do an exhaustive search. Right? I think in the back of the paper they mentioned, oh, we can do we can generate a query plan for a query with 8 tables in seconds, right? So think of like milliseconds now. Of course, the challenge is going to be they have the same problem of the way they would implement those heuristics, a bunch of if and else statements in procedural code. That's going to be a mess to maintain because it's going to end up being a bunch of spaghetti code, and we'll see the Starburst approach of actually declaring grammars in some cases of how to define the rules, and then compiling those rules into actually then procedural code that we could run. But then the developers don't have to worry about the procedural code. They sort of, in the same way they reason about SQL at a high level, they can reason about the rules at a higher level as well. As we said before, left heap trees may not always be optimal, but that they made that choice to simplify the problem. And the physical properties are basically ignored entirely in the search algorithm, and they have these sort of stopgap approaches that check the order of data after the fact to make sure things are actually still okay, which is not ideal. Okay? So like I said, this paper is over 40 years old. Pat Salinger, he got to the highest rank you get at IBM, IBM research, like technical fellow. And again, super influential, super still relevant today. And if you're building your system, like that paper right here would be the thing I would start with if you want to build a new query optimizer in this style. We're not doing that. We're doing something different. But like, if you don't take this course, then if you just read that paper and implement that's probably good enough. But again, a lot of those simplifying assumptions in this cost model are going to cause a lot of problems for us later on. And in particular, we'll see papers where, like, because of those uniformity or the uniformity assumptions and other aspects about the independence of those predicates, a lot of data systems, or almost all data systems, are going to underestimate the size output of those join operators. And if you're making bad guesstimates of what your data looks like at some lower part in the query plan, well, that's just going to get fed up to other operators who are then going to have their own faulty calculations and faulty estimates, and the problem just gets worse and worse. And even if your join algorithm could exhaustively search, your query operators could exhaustively search all possible join orderings, if you're making decisions off of bad statistics and bad calculations, then it doesn't matter. You're probably going to pick a bad join order, right? But again, we'll see how to handle that as we go along. All right, so that's it for today. I still need to assign the IBM what paper to read for Wednesday's class. Right? Monday's a holiday. I'll take care of that tonight. But the Starburst optimizer is going to be, again, the next generation query optimizer that IBM built after they built the System R1. As I said, the first implementation of the basic idea of the System R implementation for the query optimizer, that showed up in the first release of DB2, but then the IBM research team went ahead and built this Starburst thing, which still exists today. Okay? And so that's going to take us to the next phase of our timeline of starting about stratified search. And so that'll be next week, and then the following week is when we do unified search with Volcano and Cascades. Okay? Any questions? All right, again, this is hard. This paper is the easiest one we're going to read all semester. So if it's if you're like, what the f is going on, then we should talk, right? Whether this makes sense for you. Okay? Again, the paper is fantastic. It's a very similar work. It's a delight to read. The Starburst paper, not so much. Cascades, because we have the book. That's actually understandable now. But then the subsequent papers after that, again, will be based on basically those two key ideas.
Look good, brownie. Matter of fact, hold the cup. This is like that wood grain type of shit. Shout out to Blockhouse, my dogs. Get one, Big Al, Mike Stroke, Gumby, I'm not the one who be amping up the weak ass rhymes. If you to spit, if it don't rip through your mind with a sweet anticipated, orchestrated punchline like a reverse the hands of time. Get you captivated quick with the bullshit. I keep the Cadillac equipped for the long trip. I got the remedy for bitches when they start shit. Surround sound like I make them hoes fuck quick and suck dick. Crown me as the thugs in the gun. Shit, some niggas claiming that the rapping is sudden. Don't push the button, yes you motherfuckers are frontin'. You don't want nothing if it did.